So now I request Dr. R. Shivashankar Raju Garu to give brief introduction about the second person, followed by his session. Thank you.
Thank you, sir. Thank you very much for your kind consent. Uh, I, Dr. Shivashankar Raju, we are delighted to welcome Dr. Mahadevan Radhakrishnan, a seasoned material scientist and industrial expert, as a keynote speaker for our faculty development program. Dr. Radhakrishnan, sir, is currently serving as a senior manager at Carpenter Technology Corporation, headquarters in Greater Philadelphia, USA. Dr. Radhakrishnan holds a PhD in material science and engineering and has over 2 decades of experience in the field of advanced materials and manufacturing technologies. His expertization spans on areas such as shape memory alloys, high performance materials, and their application in various industries, including aerospace and energy. Throughout his illustration careers, Dr. Radhakrishnan has contributed significantly to research and development in the materials engineering, earning recognitions for his innovative approaches to solving complex industrial challenges. He has a strong background in bridging a gap between academia and industry, bringing a cutting-edge technologies and material science in the practical applications. Dr. Radhakrishnan's sessions on shape memory alloys for industrial applications promises to provide the valuable insight to the transformative roles of advanced materials in the manufacturing. We are honored to have him share his expertise with us during this program. Thank you, sir. Hand over to you, sir.
Thank you, Dr. Shivashankar. So, good evening, everyone, and I'm glad to share my knowledge on shape memory alloys with the broader team here. Before I begin, I would like to thank Dr. Srihari and his team in organizing this event. I just want to make sure that you all are able to hear my voice. If you could just give me a thumbs up. Okay. Um, okay. So, I know that organizing such an event online takes a lot of patience, perseverance, and persistence, and planning as well. So I think Dr. Srihari and his team have done a phenomenal job. Kudos to them, and good luck with the future events. With that said, I would like to begin this presentation. My intention with this presentation is to kind of not talk about the science behind shape memory alloys, but to see how science is used through engineering in industry, and how this industry has evolved over the last few decades, and the challenges faced by this industry, as well as how things get processed, as well as converted into a product at the as an towards the end user. So this is what we'll be seeing in this talk today. If you could go to the next slide, please. Okay. So you heard about me. So currently I work as a senior technology manager at Carpenter Electrification. And my current role is also equally interesting. We work on iron cobalt alloys, hyperco alloys that get used in the next generation application for electric aircrafts. So that's kind of where I'm currently focused on. I had joined Carpenter almost 5 years back, and I was in the strategic marketing team. I got the opportunity to work across several industrial verticals. And prior to that, I was with Say Smart Materials, which is where I kind of learned a lot as far as the die-tie shape memory alloy is concerned. And I entered my professional life as a senior material scientist at TDK Headway Corporation, which was involved with magnetic read-write heads. So with that, I would like to go to the next slide where we can start talking about material. So what are we learning today? Through this presentation, I want to make sure that I'm able to convey a few things as takeaways for the audience here. The audience is pretty diverse, so keeping that in mind, I have kind of highlighted select things that I would like to share on this in this space. So we would start with a brief introduction on shape memory alloys. And then we will talk about the two functional properties which kind of make it valuable in the industry. One is shape memory, and the second one is superelasticity. We will see what they are. And then in any industry where you have a vendor and a customer, you need to follow certain standards to make sure that it is acceptable for both the parties. And so that's where you have the ASTM standards and the characterization techniques that are used as part of these standards. How and what they are, we'll see as well for this shape memory alloy NiTi. And then one of the most important aspects of shape memory alloy is their use as in medical devices where the functional property of superelasticity is used. So we will spend some time on understanding how the fatigue of these alloys are extremely important. And over the last, I would say 15, 20 years, phenomenal work has been done in this space. So we'll learn a few things about how fatigue is assessed and what's the status on this topic. And then finally, we will move on to some of the select applications that are that use NiTi, and then taking it a bit further, I would say upstream. How are SMAs made in the first place? Starting from melt and all the way down to how it is converted to mill products, and then finally how it is manufactured using state-of-the-art laser cutting EDM. We'll just briefly review that. Again, it's a very vast topic, so my intention is not to delve deeper, but I want to create an excitement in the audience so that they can actually learn from here and they can go on their own individual capacity and research a bit more to understand the specifics of what is being shared here. Finally, I will end the presentation with giving you an overview of the industry, the supply chain, and at the end of this presentation, I have also listed a few websites. There are a lot, but I have selected a few of them where you can gain more information about the specific material. Next slide, please. So one thing, if Dr. Srihari is okay with it, I was thinking that because there is too much of information shared here, midway through the presentation, sometime after the ASTM standard slide is discussed, if there are any questions, we can have the first session, maybe a few minutes, and then we can have one more session at the end of this presentation. Dr. Srihari, you let me know if that works with you. Okay. So with that, let's start with the first slide here. Obviously, with any nitinol presentation, it is interesting to see the video in terms of what happens, what is nitinol, to get a first-hand experience. I got excited the first time when I saw nitinol. So I think if we could just click on these videos, these are in YouTube, so hopefully there's no ad here, but these are less than 1 minute videos. So I don't know if you can hear it, but essentially this guy is trying to dip a spoon made out of shape memory alloy, and he's seeing that he can bend it. So that's one of the aspects of this alloy. You can see how it bent. The next video. If you click on the next video, you can see that the material is deformed. It has been given a shape. And then when hot water is poured into this wire, you can see it regain its the shape that was given to it, which is what you'll see here as he's pouring the hot water. So I think we can stop here, but this is what shape memory alloy can do for you. It can remember its shape and it can come back to that original shape even after you deform it. This is unlike any other material. So this is what is unique about this material. So with that, if you go to the next slide. If we could move to the next slide, please. Okay, there you go. So what are shape memory alloys? Now, as you saw in the previous slide, these are alloys that can remember its shape even after undergoing substantial deformation. And what happens is after you deform in the cold state, which is the martensitic state, you can apply heat and it will revert back to its pre-memorized or pre-assigned shape. That's why they are called as shape memory alloys. Now, the other aspect of shape memory alloy is superelasticity. We will go into detail in terms of what these terminologies mean, but superelastic, as the name implies, it has got exceptional elastic recovery, approximately around as high as 8% elastic strain it can recover, which is what you see on the slide on the graph on the right-hand side, the blue color graph. Now, it was discovered by William Buehler in 1963. The name nitinol came because it was discovered at the Naval Ordnance Lab. That's why you have NOL and nickel titanium. So that's why it's kind of very commonly known as nitinol. There are several other systems that exhibit the shape memory phenomena, but nothing as NITI is commercially successful. NITI is approximately a multi-billion dollar, roughly in the range of $17 to $20 billion industry in itself. Next slide, please. So the question that naturally comes out is, what causes these shape memory and superelastic phenomena? So if we delve deeper, just like what you have in steel, this transformation, the phase transformation that happens in nitinol that gives these properties is due to martensitic transformation. Now, martensitic transformation by itself, it's a diffusionless transformation, so there is no long-range diffusion of atoms, and there's no chemical change. There's no change in chemical composition of the phases before and after the transformation. But unlike steel, in NITI, the martensitic transformation that enables shape memory, it's recoverable. And it's mainly because of what's called as twinning. Okay, without going detailed into twinning, I will say that if you look at the two crystal structure schematics here, these are called as the variants for martensite. So if you look at the image, the black outline is your cubic austenitic unit cell. And then if you look at the red one, that is the martensite unit cell after the phase transformation is completed. For the sake of easiness, what you see here is from cube to an orthorhombic crystal structure. But in reality, there is also a distortion that is involved, which makes the orthorhombic transition to a monoclinic structure. So that's why in the austenitic phase, you have a cubic structure. And in the martensitic, the low temperature phase, you have what's called as a monoclinic structure. Now, there are different variants of martensite, which enables the material to kind of self-accommodate. And that is the reason why you're able to see a phase transformation where there is no external change in shape despite having the phases, despite there being a phase change. How do we identify this? If you look at the optical micrograph on the right, you can see that you have grains identified as austenite and martensite. So typically, austenite would look like any other grain structure, whereas martensite, you can see some streak of lines like parallel lines, which is nothing but the twinning that's happening in martensite. So this is how you can identify it using an optical microscope. Next slide, please. So as far as NITI is concerned, the majority of our talk will be on NITI because that's the most successful alloy, right? So we'll focus on that. So there are three pathways for NITI, for the phase transformation to happen in NITI. It's dependent on a couple of factors. One is your addition of ternary elements. When you add a third element, for example, iron or copper, then you will have an intermediate phase through which the phase transformation occurs. Alternatively, based on your heat treatment, aging, cold working, annealing, cold working, aging, you will also have an intermediate phase called as R phase. So there are multiple pathways through which the transformation can proceed from a high temperature phase, which is the austenite, to a low temperature phase, which is the martensite monoclinic structure. Long story short, the path of least resistance will be preferred by the alloy. So you can actually tailor which treatment you want and how you want the transmission to proceed. Next slide, please. So we have been talking about the two functional properties, shape memory and superelasticity. So what are they and how they are kind of induced? Let's see. So shape memory is, again, the ability of the material to return to a preset shape following substantial deformation. Now, shape memory is induced by temperature. You need a temperature. You need to add heat or remove heat for this phase transformation to occur. And typically, you can go either from the high temperature austenite to the low temperature martensite, or vice versa. It's a reversible transformation. What's the advantage? Now, this particular functional property is used in actuator industry. You can see some examples down the slides. They are used as actuator springs, and you'll be amazed. You can see a lot of videos in YouTube or in the net where you can see that a tiny spring can lift some heavy load. So recovery stresses as high as 500 to 600 megapascals can be generated using this transformation. On the other hand, superelasticity is induced by stress, and the transformation proceeds always from austenite to martensite. The starting phase has to be the high temperature phase here. Only then you can experience superelasticity. We'll see that down the slides here. And there is a specific temperature called as the martensite desist, above which you will not see any superelastic effect. The material will behave like your conventional material in terms of just elastic stress strain and then plastic deformation. Now, the superelasticity, as the name implies, it can recover as high as 8% elastic strain. Where are these used? These are used in medical applications like your peripheral stents, heart valves, and you will see some of those down the presentation here. So that's kind of, I would say, these are the two major reasons why the alloy is used in medical and aerospace industry. It's also used in consumer industry, like in the mobile phones, where they are used for your camera stabilization. So there are several applications here, but I would say that 90% of the applications is in the medical device industry. Next slide, please. So as I mentioned, the following slide, please move to the next slide as well. So we will talk about the characterization of shape memory alloys here. If you go to the next slide, you will see that there are different ways in which you can characterize the alloy. But in this industry, there are three which are predominant. One is the thermal technique that you see here in the first column, where you have what's known as a differential scanning calorimeter that's used to quantify the transformation temperatures. The first chart is a schematic of the DSC. You have the heat flow on the y-axis and the temperature on the x-axis. And through this, when you heat and cool, you predominantly characterize three different temperatures: the start, the peak, and the finish of the forward transformation from austenite to martensite, which occurs on cooling, highlighted by the blue arrow. And then on heating is the reverse transformation, where again you quantify the austenitic start, peak, and finish temperature. DSE is typically used at the ingot level, or when you want to understand or determine what is the composition of the material. We'll talk a little bit more about it in the melting slide, but DSE is kind of used at the extreme upstream of this of the material manufacture. Right below this is what you see. It's called as bend-free recovery, and what you do here is you apply a pre-strain on the material in the colder phase, which is the martensitic phase. Typically, I would say around 3%, 1 to 3% strain is applied, and then you slowly start heating the material. And as I told you earlier, you generate recovery stresses, right? So as the transformation happens, you plot the deformation as a function of temperature. Now, the bend-free recovery is typically used on fine products, after the ingot is processed and then converted to fine wires or fine tubes or even fine sheets. This is the most appropriate characterization technique I would say. And as a derivative of this technique, you have the uniaxial pre-strain free recovery and a bunch of other similar free recovery tests. But these are the two predominant thermal characterization techniques that are used. On the right-hand side is your typical stress strain curve. If we start with austenite, which is on the back side of on the back end of the chart, you will see that when you apply stress, there is a forward transformation from austenite to martensite, and then when you release the stress, you get revert back to martensite, which is the reverse transformation. So you have upper and lower plateaus. These are very, very important. And when you take when the starting phase is martensite, and when you apply stress, the profile that you will get is kind of what you see here. There is also a plateau here, but this is not stress-induced transformation. But this is what is called as the detwinning of martensite. The martensite that is twinned on application of stress gets detwinned. That's why you're seeing that strain that is self-accommodating. There's too much of terms involved here, so I will not go further deeper into this. But if you have any questions at the first intermediate break, I kind of try to answer these questions here. But what I would also add here is, after you deform the martensite, the strain that you see here can be recovered when you heat it. So that's kind of what I would like to emphasize here. So thermal and mechanical characterization are the two techniques that are predominantly used in the industry. The third one that I didn't mention, but you will see in the slides to come, is micrograph, optical microscopy, where they characterize the inclusions, and we'll see a little bit more on that. Next slide, please. So this is kind of, as we delve deeper in terms of how the stress strain responses of the three phases. Like I told you, the high temperature phase is the austenite. Then you have the intermediate phase, R phase, in specific alloys. And then you have the low temperature phase, which is the martensitic phase. So how the stress strain response varies, you will see in this slide here. This is taken from a data that I researched on a material called NITI-FE a few years back. And so if we start with the austenitic phase, the bottom end of the phase, there's a typo here. This is all in Kelvin. The 0 degrees centigrade you can ignore. If you start in the austenitic phase, when you apply stress, you get pretty much like the elastic response of austenite, just like any other material. But as you lower the temperature, you are actually transitioning into the intermediate R phase. And when you apply stress, you can see that you are able to recover around 0.7% of strain, which is much significantly higher than conventional materials. And this is because of the stress-induced austenite to R phase transformation. Now, as you cool it a bit further, you are actually in a phase where the starting phase is R phase. So when you apply stress, the R phase detwins, and then the martensite starts reorienting. That is why you are seeing some unrecovered strain here. Now, this unrecovered strain can be recovered by heating the material. Cooling further, where you are still in the R phase, you can see that the martensite reorientation is progressing. You are generating more strain, and you are able to recover all these strains by heating it back to above austenitic finish temperature. So this is how the material stress strain response evolves as you start with different phases or a combination of phases. So these variation in stress strain response are kind of used across in all the applications that we are going to see. Next slide, please. So with that said, I would say that the ASTM has several standards for nitinol, all of which are listed here. There are other agencies like the Japanese JIS, I believe. They have their own standard for nitinol, as well as the Chinese standard agency. But ASTM is widely used globally, and it's kind of the gold standard in terms of the specifications that a customer and a vendor agree upon. So you can see that you have several standards like the F2063, which talk about the chemistry and other properties that need to be the impurity elements and other things that need to be expected for a NiTi shape memory alloy. And then you have the DSC that we spoke about, 2004 thermal analysis. And then you have the tension testing, 2516. And we also spoke about the bend-free recovery, which is 2082. So these are some of the key ASTM standards that have been employed in this industry for as part of a standard. With this, I just want to take a short break and see if anybody has any questions so far. We can take probably 1 or 2 questions if they are available. If not, I'll continue to proceed.
Participants can raise their hands, unmute themselves, and raise any query. Yes, sir. Dr. G. Sachinaran Reddy.
Okay, so one small question, sir. When you were doing the DSC, the heating and cooling, the transition temperature while heating is far away, cooling, this slight mismatch.
Yes.
Why this mismatch?
Yes. So if we go back to that slide, I would say slide number, page number 10, I would say, if you could go back to that. I think the question that was asked was the start. Yeah, if you could go back to that slide, please go back a couple of slides. Oh, yeah, this one exactly. So the starting and the finish temperature of the austenitic start or the martensitic start, they are not aligned and there is a shift. And that's primarily because you can see here, I didn't mention it, but I call it as the hysteresis. And that's because you have grain boundaries, you have dislocations and bunch of other things that are, it could also be precipitates that are preventing the transformation to occur at the same temperature. So what happens is you need to expend more energy when you are kind of heating it back. On cooling, the amount of energy required is much lesser. So that's why there is a hysteresis, I would say. That's why they are not matching.
Yeah, having said that, for some applications, if we want to have some precision, transformation to occur at precision temperature, will it respond like that, or with aging, with more and more usage, his behavior is going to change?
Good question. So when somebody is designing NiTi for a specific application, and again, when we talk about the type of functional property that we are referring to here, it's the shape memory. And I would also say that there is a correlation to superelasticity, which we'll see later. But the point is that when somebody is designing this for a specific application, they take into account the ambience in which the temperature, the environment in which it's going to operate, and they take into account the multiple cycles that it is going to kind of be subjected to. So with all these factors, and we have there's also a rich history which kind of helps you model what kind of shift in your temperature and your stress response you will see. We'll see that in a subsequent slide, but that's a good question, and we'll talk about that. So there will be some changes, but they all will be accounted for.
Thank you.
Mm-hmm.
Any other queries here at this point of time?
Okay. So
Yes.
Sir,
let's.
excuse me.
Sure.
Sir, you said that there are many applications. Is there any biomedical application related to shape memory alloys?
So there is a lot of biomedical application from superelastic standpoint of view, but on the shape memory side also there are certain applications. What I can tell you right now is there are some in the bone clip industry for when you have a fracture to join the bones, right? So there are some bones that nail clips, I should say, they kind of employ shape memory. And then there is, I think, there is a company that also uses this shape memory effect in one of the glucose meters. So there are few applications like this, and also probably also in the orthodontic industry, which make use of the shape memory alloy functionality. I mean, shape memory functionality.
Oh, thanks.
Yep.
Yeah.
Okay.
So can we proceed, sir? Yeah, we can
Okay,
proceed.
perfect. So good questions. And now let's jump on to the next slide. You can skip to the next slide also. Yeah, the following slide as well. So we will talk about the fatigue of shape memory alloys here. Now, fatigue is kind of pretty critical for any applications, and same thing with shape memory alloy here. But the challenge is there are two types of fatigue. I think one of them, one of the questions recently, I mean, just a few minutes ago, was how things will change with cycles, right? So you have what's called as functional fatigue, and then the second part is the structural fatigue. So these are two different things. This was coined by, I think, by German professor Egler, and it's very important that when somebody designs the alloy for a specific application, there's a good understanding of both these effects. As I mentioned earlier, almost 15 to 20 years of work has been extensive research has been performed on functional and structural fatigue of these alloys, and very important and interesting results have evolved. And still, there are a lot of unknowns. I will say that nobody has completely understood the fatigue of shape memory alloys. There is a lot of work going on. The material behavior changes depending on a lot of factors. So for us, for this session, we'll look at few things. Let's understand what functional fatigue is, what it can do, and then what structural fatigue does, and what are the factors it depends on. So starting with functional fatigue, as the name indicates, the functional fatigue means your functional property, your shape memory or superelastic response gets degraded due to repeated cycling. So if you look at the DSE, the thermal chart on the top, you can see that as you start from cycle 1, which is the red profile, a thermal profile, you will see that it starts at a higher temperature, and with cycling, the phase transformation from martensite to austenite, which is on the cooling, kind of shifts towards lower temperature. And on the other hand, I must say that the axes have changed here compared to the previous DSE. You can see that the cooling is actually the top profile and the heating is the bottom profile. Okay. So on the other hand, when you cycle it on the reverse transformation, the temperature starts increasing. The reason many researchers have explored this, and the reason they attribute to this degradation is because as you cycle, you generate dislocations, and your microstructure changes and kind of starts creating more hindrance for the phase transformation to occur smoothly. And that is why you're seeing this shift in the transformation temperatures. And this is to be expected in any application where the alloy is used. So people try to work keeping into account how to circumvent these changes. And there are ways to circumvent this. The second one, the chart right below that, is your functional fatigue when it comes to stress-induced transformation. So the chart shows your stress-strain response. And from cycle 1 to 10, you can see that that particular degradation is extreme. You can see how the degree of shift in the upper plateau stress is significant. But as you kind of increase the number of cycles from 150 to 1000 to 2000, you can see that the shift, the degree of variation has significantly decreased. So what it implies is that as you increase the number of cycles, okay, the change in the response is going to be more or less stabilized. It's going to get stabilized. The same thing happens for heating as well as for stress-induced transformation. And so this is kind of something that the designers are aware of, and they see how they can kind of get this stability, what kind of pre-strain they have to introduce, or what kind of cycling has to be done on the material. So they take into account all these things so that they can get a reliable performance of the material for that specific application. Now, coming to the right-hand side, which is the structural fatigue, it's just like your conventional, the fatigue in conventional material. So you are just looking at the failure of the material due to fatigue response from cracks, from inclusions, and you see how long of a fatigue cycle the material can survive. So if you see on the top, you can see that the testing was done after subjecting the material to 4%, not subjecting, at 4% tensile mean strain. And the one in the red box, hollow box, is a 2% tensile mean strain. So what I would say is that there are several factors that impact the fatigue testing, and your tensile and compressive stresses, the distribution of these stresses, all these things impact your results. I have summarized in the next slide on the key points that we need to remember. So there are a lot of articles out there. So if you want to delve deeper into this, please go ahead and take a look at that. It's very interesting. And the one below that, the fatigue chart below that, tells you the tests that were conducted at different temperatures. So as I mentioned earlier, you have different phases, like the high temperature austenite, then you have the intermediate R phase, and then the low temperature martensite. The fatigue response is also a function of which phase you are cycling it in. So again, there's a lot extensive work done on this as well. So the fatigue performance as such has got different factors that determine the performance. If you go to the next slide, please. So because this is a very vast topic, I definitely thought we should, and an important topic as well, I thought I should kind of highlight some of the key factors or the points to remember when it comes to fatigue testing of these alloys. So starting with the material chemistry itself, the alloy chemistry. When I say chemistry, the nickel, titanium, ratio, and then the impurity elements like carbon, oxygen, nitrogen. All these kind of have a significant impact on the fatigue of the alloy. How, for example, the impurity elements such as carbon, oxygen, obviously will kind of form inclusions. We'll see in the next slide how to identify them. They typically form carbides, oxides, or oxynitrides. And just like any other material, inclusions are detrimental. They are bad for your alloy. And so the size of these inclusions and the area fraction of these inclusions, these are two critical things that one has to look at and understand how they are in the material. And you will be able to kind of correlate the inclusion size and the inclusion area fraction to the fatigue life. Again, several studies are out there on this topic. The next one is the heat treatment that we generate, right? So the precipitates that you generate, the grain size, the texture, they all also have a good impact on the fatigue life. I just showed you a chart in the previous slide where I mentioned the starting phase is also critical. So fatigue life is also dependent on the phase. Now, the fourth point that you see here is surface finishing. So if you start with something, typically most of these alloys, because they go inside your body, they are actually electropolished and they're chemically passivated. And so you expect to have a good surface finish. Now, fatigue crack originates from the inclusions on the surface. So you have to the surface finish also plays a role in your fatigue properties. Last but not the least, the testing setup is extremely important. You have what's called as RBT, rotating beam fatigue testing, which is used, but there are also other setups where they use a diamond-like profile and they kind of test the fatigue life. The temperature at which the sample is being tested is extremely important, because when you cycle it between austenite and martensite, heat is evolved and heat is absorbed, and that heat itself can impact your stress levels. So there are a lot of factors. There's an article by Shaw and Kyriakides which details how these factors are extremely critical and important in getting good and credible results. So other factors, the sample geometry, like what I mentioned, a diamond-shaped sample being used in the industry in general, exposed by some people. And then you have the strain amplitude, the pre-strain put into this, as well as the combination, the distribution of compressive versus tensile stresses. All these things impact your fatigue characteristics. So these are not comprehensive, but at least some of the key points that one needs to remember when it comes to the to understanding the fatigue of these alloys. Next slide, please. So I just mentioned about inclusions. So inclusions are very bad. And when it comes to nitinol, there are predominantly two families of inclusion. One is the carbide, and the other one is the oxide or oxynitride. For carbides, the chemistry is typically like TIC, titanium carbide. It is a titanium carbide inclusion. And it's usually, it appears like a black particle, like what you see in this image over here. These are all optical images. You can see the scale, 10 microns. So those are your inclusions, carbide inclusions, the one that appears in the black contrast. The lighter one, the light gray, is actually the oxide or the oxynitride. And both are bad. And you can see when you continue to process the material, because you're starting from an ingot, which is typically either 12-inch or 14-inch, and then you hammer it down, forge it down, and then into billets, and then from there you are drawing it into very fine wire. Imagine that wire is going inside your body, wire or tube. So you can imagine the amount of reduction this material undergoes. And so what happens is, these inclusions like oxides and carbides, they can elongate, they can break up, and they can form what's called as stringers. So if you see the elliptical region that I have highlighted, that's actually a stringer. That's because the inclusions have broken down as you continue to process them, from hot working to cold working and back and forth, So these are some of the key things that one needs to look at and understand whether the material is going to perform well or not. It will give you an indication. So people actually characterize the inclusion size and the area fraction, and they tell in their specification. Even ASTM F2063 also calls out for this, but that's only on hot rolled products. There is no specific information on cold rolled or cold worked material, and that's what is critical. Okay, so I will leave it at that, but this is just to show you that these are the different types of inclusions that are recognizable from your optical image. Next slide, please. So one of the attributes that is important for your fatigue property is the precipitates. So if you look at the NITI system, there are different precipitates that can form, and typically there is a phase diagram that I have kind of that's going to come up in the upcoming slides. We'll talk a little bit more about that. But in the NITI system, the nickel-rich side has a solvus that kind of enables you to control the chemical composition as well as the properties through aging. And this particular example of the time temperature transformation diagram is for a specific composition of NITI alloy. For all the charts and for all the images that I have presented in this presentation, you can see in the bottom right corner the reference from which it was taken. So feel free to kind of explore that. And this is from a specific alloy where it shows as a function of temperature and time what is the precipitate that you are kind of going to get. Long story short, I will say that nobody ages in the industry this alloy for 1 hour or 10 hours. So those are all practically not feasible, right? So typically it's within few minutes, a few minutes, I would say. I'll leave it at that. I won't go into the details. But I would say that one should aim for Ni4Ti3, nickel-rich precipitate, which is approximately, let's say, few nanometers in size. And it should be in a position where it is able to exert some stress in the matrix and strengthen the matrix, I would say. I would leave it at that. So that's kind of what you learn from these diagrams. So it's important that for the specific alloy that you're looking at, you're familiar with this. Next slide, please. Okay. Applications. I think we have another 10 more minutes, I guess. So this is the interesting part. Now, both shape memory as well as superelasticity has its own set of applications. We'll start with shape memory. Shape memory is predominantly used in the aerospace and in the industrial sector, consumer electronics as well. And some of the examples that you see here are, what are known as frangibles from a company called EBAD. They are used in aerospace applications for separation of for a satellite, for another things. You can go and explore what kind of applications they are used for. But this employs the shape memory functionality. The one below that is from Sales Getters. They have an industrial division that caters to automotive and other sectors. And you can see here, these are nitinol springs that are trained to kind of exert stresses, the recovery stress, and they're actually trained to sense and actuate at a specific condition. So these are some of the examples of shape memory. On the right hand side is all super elastic application, which is predominantly used in the medical device industry. There are numerous applications, but I have just highlighted 3 of them here. If we start with the first image, it's a self-expanding stent. Nitinol stents are typically used in peripheral vascular applications, right around your, near your ear or near arm, legs. So that's kind of peripheral, not in the heart, coronary. So these are all peripheral applications. And if you look at the second image, it's a heart valve. And this is actually a very strong and a growing market. These are heart valve frames that are used to replace one of the 4 heart valves. The one that you see here is typically used in is used to replace your aortic valve. And transcatheter aortic valve replacement is one of the well-established market that uses nitinol. And then on somewhere in the middle is what you see, the nail clips that I was talking about, which is predominantly super elastic, but they can also use shape memory functionality. So these are the several applications that use nitinol. One thing I forgot to mention in the fatigue is, if you could just go back to the previous slide, I think slide number, let's say 14. Sorry. I want to mention something here, the previous slide. Yeah, here. So unlike your conventional material where you have stress versus number of cycles, in nitinol, they plot strain versus number of cycles for the simple reason that if you look at the stress strain response in the bottom left corner, you see that at a particular stress, the strain increases. So that's the reason why they don't go with stress, but they go with strain. So varying strain, and then they look at the number of the life cycle of the product is evaluated. All right, thanks. If we can go to the slide after application, slide number 20. Yeah, the next slide, please. Yes. So this is actually something very important, and it actually goes back to one of the questions that was asked earlier. The stress temperature correlation or the equivalence is also very important. This is also known as the Clausius-Clapeyron equation in thermodynamics, right? Relation in thermodynamics. So what happens is you can quantify the stress that is needed as a function of temperature. And so what happens is in real life application, where you are subjected to harsh conditions, right? Temperature changes, the stress may change as time evolves, for that particular application. So this particular correlation is extremely important for the designer to understand when he or she is designing the product, right? So what you see here on the left is the stress strain response at different temperatures, and you can see that there is a shift in the onset stress, and then upon cooling, you can see that for the temperature at which these are recovered also changes. So when you plot that on the right hand side, you will see the stress versus temperature plot. You can see that there is a specific linear relationship, which probably may not be actually linear in the strictest sense, but for all practical purposes, right? You can see that there is a linear correlation, and this kind of tells you how much of a shift or how much of stress you can expect with a 1 degree shift in temperature or so on and so forth. So that's why this is extremely important. Next slide, please. So the last few slides, we'll talk about the manufacturing of shape memory alloys. If you go to the next slide, we'll start with how it gets melted. So there are, I would say, 3 techniques, actually 2. One is VIM, vacuum induction melting, which is what you see on the first top left corner. And then you have what's called as a vacuum arc, melting slash remelting. So nitinol is usually melted either through VIM or VIM VAR or VAR only. There are other players who are exploring new technique like plasma arc melting, I would say. But historically, these VIM and VAR are the most widely used ways to melt the alloy. It's actually a challenge to melt these alloys for a reason which you will see in the next slide. But once you melt the ingot, you can see on the rightmost side, that's how it looks like. That's how it looks like after it comes out of a VAR furnace. And then the ingot is then forged. You can see it heated, and then subsequently it's forged. And after forging, the forged billet is kind of peeled, and the rightmost image on the bottom shows you peeled billet. So this is how it translates from ingot to billet. And then subsequently, if you go to the next slide, please. Okay, so I was mentioning that it's a challenge to melt nitinol. Why? Let's look at the phase diagram. So if you see here, the nickel and titanium phase diagram, you can see here that roughly at 50-50 weight percent, you can see how narrow the NiTi phase field is, right? So maintaining a composition control is extremely difficult. And what makes it complicated is, you can see the chart on the right. What you see there is the variation of nickel percent and the nickel titanium ratio on the top. You can see that, and how the martensitic start temperature changes. So you can see how steeply it flows, it falls, right? So that's why maintaining a chemical homogeneity in the ingot at industrial scale is extremely challenging. And people have been able to kind of work around it. They have come up with innovative ideas, and they have kind of been able to melt it. So when somebody tells you, asks you a question, what's the chemistry of the NiTi alloy? It's very difficult to answer that. And rather, the question should be, what is the transformation temperature? So that's why if you look at the ASTM standards, F2063 and so others, they will insist on specifying the transformation temperature. Most of them go with austenitic start or austenitic finish temperature while specifying their alloy. So if somebody says, I can give you the chemistry of NiTi alloy, it would actually not make much of sense for us. Because of the sensitivity of these nickel-titanium ratios. The other thing I want to point out in the phase diagram is, if you look at the nickel-rich side, you can see the solvers. There's a slope over there. And what that indicates is, I was mentioning about the time temperature transformation diagram, right? So based on this particular slope here, you can actually tailor what kind of precipitates, what size of precipitates, and what area fraction you can generate. So that's why you can actually generate precipitates in a nickel-rich alloy. You can control things. Whereas if you look at the titanium-rich side, it's pretty much straight. Like, there is no slope here. So on the titanium-rich side, you do have Ti2 Ni precipitates, but that doesn't make any. That's not of much use in terms of controlling, the functionalities, I would say. So these are a couple of things that I thought I should share as far as the alloy system is concerned. Next slide, please. There are a few other systems that also are commercially produced. NiTi iron, NiTi cobalt, and NiTi copper, as well as NiTi chromium. So these are some of the ternary alloys that get produced, and there is extensive research being done at several universities and research labs on NiTi hafnium, high temperature shape memory alloy, and NiTi palladium for applications in aerospace. So the chart here, this is just for reference, and the reference is given in the bottom right corner. It gives you an overview of, when you add these ternary element, does the transformation temperature increase, decrease, or does it remain unchanged? You'll get to see from here. Next slide, please. So we saw how the ingot got converted to billet. And after that, what happens is the billet gets rolled over into a coil, which is what you see on the top left corner, or it gets converted into bars or rods, I should say, which is the one on the right-hand side. And at this stage, after it gets converted to coil, what it generally undergoes is mostly it undergoes a cold reduction. So the coil is converted, the wire that you see over there, it gets converted into fine wires, which are then used for different applications. And then the bar gets rolled down to a specific diameter, and then you will see that it gets it's hollow, like the bar becomes a tube or the rod becomes a tube. So there is gun drilling that is done on these alloys to remove the inner part of the material and to get tubes like what you see. You can see the variation in the tube sizes. And imagine these tubes are the ones from which the stents are being cut, laser cut. And these are the ones that go inside the arteries in our body. So you can imagine, I wanted to I wanted the audience to appreciate starting from such a big ingot and how much of a reduction we are putting in. And this actually goes inside your body. So the buy to fly ratio is pretty high. Okay. Next slide, please. So I didn't go into the details, but this will be of interest for many of you. This is more on the manufacturing side of the device. So there are a lot of contract manufacturers who actually employ laser cutting, EDM, milling, and a bunch of other techniques to kind of create the end devices, like stents and whatever you saw earlier. So this is taken from a company called Resontics, and they have listed the pros and cons of each of these techniques. So this is just again for information. Next slide, please. So this is we're coming to the end of the presentation here. I would say that it's important in any area that we are working on. We need to know how the industry is, who are the players, how things evolve. So with NITI, I thought we should kind of have a look at the supply chain here, starting from melting. There are a lot of players, but I just listed here the top few players in each segment. So starting from melting, you have players like Confluent, Fort Wayne, Furukawa, Resonetics. And then when it comes to conversion, you have players like Carpenter, ATI. And then you have intermediate processing where the coil gets converted to wire or the rod gets converted to tubes. So you have a bunch of players over there. And then you have the contract manufacturers. Now, these are the guys who actually make those devices using laser cutting, EDM, and all those tools. And then finally, you have the OEM. The OEM, some of them may also do the processing, making the devices in-house, while many of them may outsource the work to contract manufacturers. But the final step of passivation, cleaning and passivation and all those things, some of them may do it in-house. But those are the big names that you see in this industry. And as I mentioned earlier, NITI by itself is roughly in the ballpark of $17 to $20 billion industry, with all these applications and it continues to grow in double digits. Last slide. Because I would not be able to share everything in this 1 hour presentation, I thought I should actually at least list some of the websites where you can find some resources. Anybody who is interested, please feel free to go to these websites. There is a wealth of information here, and you can learn a lot more from these websites than from this 1 hour presentation. So with that, I will kind of wrap up this talk here, and we can open the floor for questions.
Yeah, participants, you can raise your hands and ask your any queries or questions you have. Yeah. Yeah, please, sir. Dr. Satyanarayan Reddy.
Okay, sir. Actually, stent means I thought it's like a spring. But you said that some tube is processed further into the stent. So can you clarify that actually?
Yes. So there are different types of stents. You have braided stents where you actually use wire and you can stitch it to form a stent. But most of the stents, even the heart valves, what they do is they take a tube, fine tube, and then they laser cut it. So there are a lot of videos on the internet where you can see how they actually make a stent. So they take a tube and then they laser cut a pattern. That is how it is done. So most of them use tubes, But there are also some stents, braided stents, where braided wire, where they are used for making a stent out of wire.
Okay. Just one
Mhm.
last question. The titanium, basically titanium gets oxidized severely. That's why it is, as you said, is vacuum induction melting or vacuum arc melting to make the bars, and
Mhm.
they do it. That's right. That's the melting part. After that, the forging, rolling, or extrusion to make
Mhm.
it bars is done in the open air room. They heat
Yes.
it furnace, ordinary furnace, and then they do the extrusion or what it's to produce the bar, or extrude it if you want the hollow tube, things like that. Okay? So but the heat treatment is again done in vacuum heat treatment furnace. Is that right?
No, not necessarily. So what happens is that the melting is done in vacuum. In fact, you will be surprised, like, because despite 50% of titanium, people are still able to do induction melting in a refractory crucible, right? So that's something different. But my point is that uh, after the ingot is melted, all the forging and all the heat treatment is done in open air, because you have titanium oxide. It forms a protective layer. And what happens is that I also mentioned that there's a high buy to fly ratio, right? Which is very important to note. So your point is absolutely valid, because when you heat nita in open air, it forms oxide. And that's why after every stage, they kind of remove the topmost layer. They kind of peel it after forging, like peeled billet I showed you. And sometimes they will kind of after they draw it down to fine tubes, they will chemically etch it, and they will electropolish it to remove all those oxidized layers. So that's kind of what they do. But apart from melting, all the subsequent hot processing steps are always done in open air.
Okay. One General Electric they invented the short pinning process. So
Mhm.
in order to introduce the compressive stresses into the turbine blades. So once you do the short, they're not titanium glass, but just in order to increase the fatigue life, they have patented a process called short pinning. So basically, they short the glass beads over the surface of the turbine blades. So
Mhm.
they're using the compressive stress so that the fatigue cracks will
Yep.
crack only under tensile conditions. Okay. So what my
Mhm.
question is that for your medical implants, which are very, very critical life-saving things, do you
Mhm.
also do anything like short pinning to extend its?
Yeah. Yeah, good question. So I would personally not know if such a process is followed by specific industries, but in general, I know that there is research going on laser short peening, and the one that you just described. I know there's a lot of activity going on over there. But to the best of my knowledge, I would say that you are right that you need to have compressive stresses on the surface to kind of benefit your fatigue response. You don't want tensile stresses. That's absolutely true. But I am not aware of somebody kind of doing this, at a commercial scale. Maybe it might be a proprietary process by somebody, but I'm not aware that it is kind of, established as a standard process.
You mentioned laser pinning. What did you say? Laser short.
Yeah, laser pinning. I know that I have seen several articles where they do using laser, they kind of bombard the surface to exactly create compressive stresses. I know they kind of do that as well.
Okay, like probably they vary the heat
Yeah,
flux to
yeah,
something.
yeah, yep.
Okay, sir. Thank you very much. Thank you.
You're welcome. Yeah.
Any
Hello,
other
sir.
query?
Yep.
Hello, sir.
Yeah.
Hello.
Go ahead.
Sir, thank you very much, sir. It's very wonderful session to know about shape memory alloy. Sir, I have question regarding is there any specific particular test to confirm that our shape memory alloy reached to functional fatigue? Do we have any test?
Do we have test for what? I didn't get the last word. For what? I'm sorry.
Functional fatigue. Our shape memory alloy reached to Functional fatigue.
Oh, functional fatigue. Okay, got it. I see. Okay. So the only way for when you talk about functional fatigue, so one of the things that I mentioned was using DSC, but then I also had shown about there's another way where actually it's called as uniaxial pre-strain free recovery, if you will. What that does is using that also you can cycle it, but those are all customized instruments which companies have, they have developed on their own, and using that you can actually do exactly like what you do with an RBT, a rotating beam fatigue tester, right? So you can develop your own, customized instrument. There is an article which says Getters had published, where you can see how they test the functional fatigue of shape memory alloy. So essentially they heat it and then they take it to, they cool it to Martensite and then they heat it. They repeat this cycle up and down, and then that will give you the functional fatigue response of that particular shape memory alloy. Because you were saying specifically to shape memory, that's what I'm saying. But on the super elastic side, of course, it's your your typical stress strain cycle.
Okay. Okay, sir. Thanks.
Yep. Any other questions? If not, I think we can wrap up this session, Dr. Srihari.
Yes. Any other questions, please? Yeah. Okay. I would like to summarize this session. We extend our heartfelt thanks to Dr. Mahadevan for delivering an informative and engaging session on shape memory alloys. The presentation began with an overview of shape memory alloys, highlighting their remarkable ability to return to a pre-assigned shape after deformation upon heating. Okay, so we have seen some good videos on those. Then the concept of superelasticity, where shape memory alloys like nickel titanium can endure significant elastic strain up to 8%, was also thoroughly explained. Dr. Mahadevan traced the discovery of SMAs and discussed how materials such as nickel titanium alloy, nickel manganese and gallium alloys, copper, zinc and aluminum alloy exhibit their fascinating behavior. Detailed graphs and comparisons with materials like stainless steel underscored the superior properties of SMAs, making the technical aspects very clearer for us. The session further explored the characterization techniques used to analyze SMAs, the ASTM standards guiding their applications, and the fatigue behavior under repeated use. The practical insights into their industrial applications, spanning to different practical applications like medical, biomedical, as well as different industrial applications. The manufacturing processes were shared comprehensively, and the relevance of SMS across sectors have been discussed. Once again, I, on behalf of the organizers, thank Dr. Mahadevan for his expertise and being it is a US time early morning for him in the office on the first day of the week. He somehow adjusted his schedule for us and providing such a thorough exploration of this cutting edge topic. His presentation offered both technical depth and real world applications, leaving us with a better understanding of the significant role of shape memory alloys, which play in the modern engineering. Thanks a lot, sir.
Thank you, Dr. Srihari. Thank you all.
Thank you.
Participants,
you can stay for some time. We'll share the feedback link.
the link is already shared in the chat box. And
I request all the participants to be in the Google Meet session continuously so that we can track your attendance and we can also take the session-wise feedback. It is very important to get the ATAL certificate. Yes, sir. Sheikh Basha. Yes, please. You raised your hand, sir.
Okay, sure, sir.
Anything else, sir?
No, sir.
A small thing to mention regarding last session also. I mean, session 1, only few people still left to submit their feedback with us. So please go through the previous feedback link and submit your attendance there. And make a note that don't forget to select this corresponding session to the corresponding day, as well as the resource person. Please select wisely. Thank you.
Once you submitted feedback, you can leave the session, and we'll meet tomorrow at 6 p.m. We'll be sharing the details tomorrow in the WhatsApp group.
Sir, after fill up the feedback, there is no confirmation coming to mail. Okay, na?
That's fine, sir. It will be noted.
Okay, sir. Thank you. Nice one.
Thank you, sir.